all set. Okay. Try to stand. I'm stuck here behind the desk, but I called it integrating design rather than integrated design because these designs don't integrate themselves. It's up to us to make sure it's an integrated process. There we go. So as an engineer, I really want to come up with a formula for everything so I can solve it. So it's the integral design, and the ultimate result hopefully is optimized performance. So we're going to go through the ways to get there, try to be as practical as possible. So the biggest thing I think you can do is work with your project managers, architects, for early analysis. There have been too many times when I've had somebody come to me with a model that's already 95%, or a design that's already 95% complete, and ask me to do an energy model, and it's too late to change anything. And if our goals aren't met, there's nothing we can do about it. Yeah, so establish energy goals, involve all the trades up front so everybody knows what we're getting into, and as an energy modeling professional, you challenge your colleagues to push a little bit so we can get that optimized performance out of the building. Click twice here. There you go. So the question is, why model? And of course the obvious answer is we're really, really ridiculously good looking, right? But that's really a question that a lot of project managers don't know. They just think we need to model a project, but why do we do it? I don't know. It's just kind of the thing to do. So challenge your project manager right up front. Why are we going to model this? What do we hope to gain from it? If they don't know, kind of show them the benefits. And sometimes maybe it's not worthwhile doing an energy model. We're not going to be able to influence the building envelope, the mechanical, electrical systems, so we just don't even need to do it. But some of the reasons we'll do it, sometimes an owner requires it. Could be energy performance or just other reasons. And then just to optimize the design. There's a lot we can look at architecturally, mechanically, electrically, just to make the design better from an energy perspective and from just a building usage perspective. And then ultimately certification. A lot of buildings are requiring LEED certification or Green Globes or EPAC, Energy Star, whatever it might be. So you need to be familiar with that. And finally, you need to push for measurement and verification, M&V. You need to find out how these models are doing, if our assumptions are right. A lot of knowledge that can be gained from actual data. And then energy audits and retro-commissioning. Those are kind of a big deal these days. There's a lot of existing building stock. IDL has showed us some presentations about that. You need to go out there and retrofit these buildings. So I'm a kayaker, and I like to relate everything I do to whitewater. So I'm thinking, I don't go into a big rapid without knowing where I'm headed, having a plan in mind. Kind of pick my lines. This is where I want to end up. Same thing with an energy model. This is the ultimate goal. We're going to get there by going through this process. But it never happens that way. You're going to be pushed off your line. So be flexible. Be ready to adapt your model to changes in design. And then make good assumptions up front so you're not surprised at the end. If you don't know answers, talk to your architect. Owner, if you can. Owner is going to know his building better than anybody. But then after that, it's a lot of guesswork. You can use ASHRAE, LEED, past experience, whatever, just to get some of those assumptions on your model. And make sure you document those assumptions because they have a big effect on the modeling outputs, and you're going to need to be able to back that up at some point. So I'll take you through the general project timeline. I think the modeling process follows pretty closely with a typical design timeline. We'll start off with the new business development. A lot of times we can do a quick model up front to help us get a job, or in the case of an existing building, we look at utility bills and things like that. just to discover where the opportunities are, inform the owners. And then the schematic design is a real high-level analysis for comparing big things quickly. Design development, we move into more systems, pretty mechanically heavy, trying to optimize systems, compare different systems still. And then by construction documents, we're just making final tweaks on the model. It could be control sequences, whatever, trying to optimize the systems in place, and then ultimately documentation of the results. And then measurement and verification, how did our predictions do, were we close? I'm not going to talk much about the business development, but like I say, new buildings, sometimes it's an energy model with one of the modeling softwares, eQuest, Energy Plus, whatever. Sometimes it's just quick hand calculations, get something off to the owner who's making the decisions here for your proposal. And then for existing buildings, I think the best way to go into that is to get their utility bills, put them into something like Energy Star's Portfolio Manager, and see where that building stacks up against existing building stock. That happens to be our billings office. But you can get a real quick feel of where the opportunities are. All right, so let's get started. We've got a project in the door. First thing we need to do is get the team together. And as many people, or as many trades represented as possible is ideal. So get your architect, electrical, mechanical, plumbing, contractor, owner, whoever is willing to join you, get them together and set some goals for the project. It could be a certain Energy Star score. You can pull typical EUIs off of Energy Star, Energy Use Index, the energy used per square foot. Could be a percent better than 90.1. We'll talk about that a little bit later. And don't forget about the functional goals. Sometimes we're all about the energy, but we need to remember that the building has to be used on a regular basis, and people need to be comfortable and things like that. We need to set some timelines for all these tasks, make sure everything gets done, and hold everybody accountable. Like I say, enlist everybody you can, challenge your colleagues, understand the climate you're going into. That's a big one. Different strategies for different climates, same with building types. And then pick the tool for the job, whether it's an energy model, a spreadsheet, weather analysis, any number of things. These are kind of some of the basic things we start to look at in schematic design. And architecturally, big things like orientation, what's the envelope made out of, how much glazing are we going to have, where is it going to face, where are views, things like that. What's the basic geometry of the building. And some of that the energy model does a good job informing if we want to maybe quantify the savings between different insulation thicknesses or something like that. Orientation is something that doesn't have a huge impact on energy sometimes. Sometimes it does, but a lot of times we want to look at prevailing winds and sun angles and views and things like that, and that might have more of an impact. So look at the architect. Mechanical systems, a lot of times we're trying to pick which system we're going to go with. So we make some broad assumptions on what those systems are and maybe do a quick cost analysis on which one works out better. Same with electrical, pretty broad ideas. And then establish your energy goals. Like I say, federal jobs are requiring at least 30% better than 90.1. A lot of them are a lot more strict than that, so know what you're getting into. Sometimes it's pretty challenging, especially in warmer climates. Oops, not too far there. Okay, so some of the assumptions that go into it, like I say, owner input is real important. As much as you can get from the owner, put that into your model, your assumptions. Architects know stuff that might be helpful. 90.1 User's Guide has a lot of schedules and kind of average usage for buildings and things like that. Know your code minimums on everything. Be able to talk to the engineers and architects on envelopes and mechanical efficiency, studying power densities. Be conservative up front. We don't want to promise the world and not be able to deliver at the end, but try to be as accurate as possible too. And the design will change, so get ready for it. So here's an example of understanding your climate. We did a number of different border stations throughout the country. It looks like we're missing some there. One's up north. The blue is a southern border station in southern New Mexico. The red is a northern border station in northern North Dakota. And you can see the heating is, there's a big difference in there, a lot of heating up north as you'd expect. But what you don't notice right off the bat is that the southern border station uses a lot less energy if you add up all those bars than the northern border station. So when we're looking for savings, the HVAC energy is a smaller fraction of the total energy use. So we're going to have to be a little more creative with how we save our energy if we're trying to meet our energy goals. This is kind of the building use component of it. A few examples, not all from our area, but they give you some idea of where the energy is used in buildings. Big box retail, so there's no refrigeration. It's all lights really. There's a little HVAC energy, but the majority is lights. That one, they actually happened to shut down their outside air dampers, so that helped the energy use too, but it doesn't meet code. Large office, a little bit more evenly distributed. When you get into supermarkets, there's a lot of refrigeration load. This one's actually kind of light for a supermarket, I think. You might be looking more towards 50% or 40 to 60. So yeah, know what you're getting into. Some building types will be easier to save energy than others. If there's a lot of process loads, it's pretty tough to save energy. All right, so now we need to choose the right tool. How are we going to analyze this? We can use weather data. There's the TMY3 data set out there, TMY2. Those are compilations of actual data from past years that they've taken what they determine to be the most typical month and compile it into 1 year's worth of data. Then there's other websites like Weather Underground, Weather Analytics, where you can either download your own weather file or your own weather data, or a pre-formatted weather file that you can just plug into your model. Sometimes past experience is enough. In this past project, it went like this, so maybe that's all we need. Do kind of the same thing. Yeah, don't be afraid to use spreadsheets or hand calculations, even some rules of thumb early on. And then, of course, the energy modeling software. This is an example of a TMY3 data set. I plotted the dry bulb temperature, the dew point, and wind speed. And it's a lot of information to take in right away, but it does give you a good idea of what the climate's going to be like. This is a project we're working on in northern Michigan, and trying to determine how much we're going to have to dehumidify. So the orange there is the dew point. So above this red line, we figure we're going to need to dehumidify the outside air, otherwise we're adding humidity to the space. So there's a fair amount of time above that line, so we need to be prepared for that. You can also look at peaks and valleys of the temperatures and get up to just above 90. So it's not too warm out there, but it does get down below 10 below on occasion out there. So you need to be prepared for both ends. This is really easy to do from energy modeling software. Just plot it out to Excel, and that goes in really easy. This is a Climate Consultant, which is another free software. Plug in your data set, and it gives you some rules of thumb. Above a certain line on the site chart, you're going to need to dehumidify, and then below you can use some evaporative cooling and all sorts of little rules of thumb on there. If you haven't checked out that, it's probably worthwhile for some early analysis, range roses and such. All right, so energy modeling software, there's a lot of debate about which one's best. They all have different capabilities. Some are supported by government, others are private. A lot of modeling software out there. How do you pick the right one? my thought is that the modeling software is all pretty accurate as long as the inputs are accurate. And so your proficiency with the software is more important than the actual software itself. So make sure you know what your inputs are doing. But you do need to consider the capability of the software and the flexibility. Some just come with box systems and you can't really change them. Others are a lot more flexible. You can build them up component by component. Something to consider is time versus the accuracy of the model. Sometimes you can spend a lot of time on the model, get it real accurate, but do we really need to do that? And the budget. Some of these are pretty expensive programs. And learning curves, some are easier to pick up than others, and some are supported better than others. So let's look at what I consider to be the four main ones, and maybe it's just because these are the ones I have some experience with. eQuest is, I think, by far the most widely used program. It's free. It's a DO2-based engine. DO2 was built probably 30 or plus years ago by the Department of Energy, and was supported up till, I don't know, 5-10 years ago, and they dropped it for Energy Plus. But it's a tested engine. It's not very flexible. You get what you get out of it, and then you have to kind of figure out workarounds and spreadsheet calculations and things like that. But yeah, it's free. There's some pretty good forums out there for figuring out how to do stuff, but there is no support directly from manufacturers. Energy Plus, like I say, is the new program sponsored by the Department of Energy. Very flexible. They basically took DO2 and they made it better, made it more flexible. They improved the Fortran code. Very accurate, free software. It's kind of slow to run. It's hard to jump into. There's no interface right away. There's a couple of third-party interfaces that do all right, but there's a pretty steep learning curve to it. But it does show promise. There's Open Studio by the NREL and Symergy from Lawrence Berkeley that I think is still in the beta phase that shows some pretty good promise. And then I kind of group Train, Trace, and Carrier's HAP together. Proprietary software, both have pretty good interfaces, good support. Takes a while to run. eQuest is by far the fastest simulation engine I've seen. I'm not sure how they do it, but it's pretty nice when you're calibrating a model or something to just be able to run it over and over and get to where you need rather than wait 5-10 minutes for the model to run. IASB is one that our company has started to look at. It's probably the most complete package out there in terms of daylighting and converting from Revit to an energy model or SketchUp or whatever it is. They have Radiance plugin and CFD analysis, things like that. Pretty flexible, very expensive. Good support, but we're still just getting started with that. So this is an example of when your energy model can't solve your problems. This is a VRV system, VRF, variable refrigerant flow, and they do heat recovery. So if one room is in heating and others in cooling, they can kind of recover some of that heat. So you go into eQuest and you get your hourly heating and cooling loads, add them up, and get your totals. But it's real easy to spit these results out into a spreadsheet. Don't be afraid to do that. Do the side calculations when you can't do it in the program. Another example of an architectural analysis we did early in a project. We're trying to decide if we wanted a lot of thermal mass on our building. In general, thermal mass tends to have a flywheel effect on the heating load in the building. So your peaks aren't as big, and it delays the heat transfer a little bit. So in cooling mode, this is a project in southern Nevada, kind of in the high desert. It gets up to about 110 on our design day, and the green line down at the bottom is a typical wood frame wall. I think we have an inch of exterior insulation in R19. And so you can see the peak it's a pretty high peak, and it's maybe an hour off of the outside air temperature peak. But the red line is 8 inches of concrete, CMU on the wall, on the interior with insulation on the exterior. And that delays the peak load about 5 hours. And so by that time, our temperature peak occurs at free in the afternoon, and doesn't get into the building until say 8 o'clock at night when nobody's there. And now we can start looking at night flushing and clearing some of that out. So it looks like a good deal from the cooling standpoint, but let's look at heating. So same issue here, except we're looking at the valley here, and the minimum temperature happens overnight at 6, 7 o'clock in the morning, and doesn't hit the building until about noon. But at noon, your building is full, and you're going to have to start heating to make up for that. So on this particular project, we actually had more heating degree days than cooling degree days. We found it was more or less washed with the thermal mass in there. But there are some cases where you have a lot of cooling load, or maybe that's a good idea. More SD level analysis. This is with our IASB software. This is just kind of a rough idea of a concept for a visitor center, I think. Not even close to what it ended up looking like, but it just gives you some idea of what's actually going to happen. The idea was that we'd have these vaulted ceilings, and the heat would kind of work its way up through the open windows, kind of a natural ventilation flow through the building. And so this one over here, that's the velocity, the air velocity in the space. And you can see it is doing that. It's kind of coming across and going up out the window. So you get some of that natural ventilation effect. And then when we're talking about naturally ventilating building, it's sometimes hard to figure. ASHRAE 62.1 has some standards for how big your opening has to be for a certain floor area, or you can calculate it on your own. So this IASB will do that. It gives you kind of your natural ventilation through each of these windows at different wind speeds. So maybe your openings don't have to be quite as big. And you can kind of look at if it really will work for you. This is ugly, but this is the language that owners speak sometimes. This is life cycle cost analysis. I encourage you to look past the first cost and simple paybacks. Look at the life of the building, whatever that might be, 10, 15, 20, 25 years, and discount it in terms of where they could invest their money elsewhere, and interest rates and fuel escalation and maintenance. Owners will want to see that, and you're going to have an easier time justifying spending a little bit more if you can show them that it will pay back in time. So now our results. And I wanted to just throw this one up here just to watch the architect's eyes kind of glaze over. This probably isn't the type of result you'd show it to your architects who want to dumb it way down, right, and put all sorts of pretty colors in there. No, but seriously, keep your audience in mind. Maybe an engineer or somebody would like that kind of data plotted out, but most people don't like looking at that. Make it easy to see. Life cycle cost, be fluent with financial terms. And remember, schematic design results are order of magnitude. We're not talking exactly what we're going to use at the end of the project. Good for comparison only, really. And so once we've got our results, figure out some way to inform the design team where we're at, where we need to go. Hey, we're not quite there. Need some help from electrical. Can you help me get there? It's interesting, this ASHRAE Appendix G, it's a 90.1. Appendix G is the standard that helps you develop your baseline model and even your proposal a little bit. Their quote at the very beginning there is, neither the proposed building performance nor the baseline building performance are predictions of actual energy consumption or cost for the proposed design after construction. So they're saying they don't have much confidence in the energy models at all to predict actual usage. So if you're going to do that, be real careful. Know your assumptions. Careful what you promise. All right, so we move into design development phase. We're starting to deal with actual equipment. Designs are starting to make their way into paper. And if you look at that integrated design chart that you see at the IDL, a lot of that work, or most of the work, has to be done up front. And then as you head into CDs, we're just getting things on paper. There's not a lot of design work being done. So We did a lot of work with SDs, kind of comparing big ideas. Now we're refining them. So architecturally, we're starting to look at shading and glazing quantities, glazing types, that sort of thing. Getting daylight into the building. And mechanically, system interactions. Different architectural features and things like that have different effects on mechanical systems, and resizing systems becoming more real. And we need to optimize that and work at our controls. Electrically, it's always been a struggle trying to get our lighting power density numbers from electrical engineers, because there are so many lighting fixtures that go into that lighting power density, and they don't know that final number until it's all designed. But keep bugging them, get some numbers out there. And then daylight harvesting strategies, that's a big one that can have a big effect on your energy. This is an apartment complex we did on Twin Falls. We looked at shading windows on the south side, and in our climate, there's a lot more heating that we need than cooling. And so when we're shading, we want to be careful not to block out that sun in the winter. Any of your architects will tell you that, if you get it just right, you get sun in the winter and it's blocked in the summer. But in this particular project, we found that no matter how much we shaded, our energy was increased. So taking away those shades actually helped us. It just happened to be that way for this project, but yeah, you want to make sure you get that heat in. Cooling, it might, adding the shade will increase your energy maybe, but it also decreases your load on your mechanical equipment. So there's a trade-off there. If you can reduce your mechanical equipment, the owner's going to like that too, and you may get better efficiencies out of it. U values on glazing almost always helps performance, but just be aware of those interactions. We talked a little bit about daylighting. Just keep in mind when you increase daylighting and glazing, it does have some negative effect on your building heat transfer, because no matter how good your glass is, it's not going to be as good as a big wall with external insulation, and so you're going to be increasing heat transfer. But there is a balance point there. You start adding glazing, nobody wants to work in just a solid dark box. So at some point, you're saving energy by dimming lights, but then at some point you start increasing your energy usage a little bit. And keep in mind the intangible benefits. They may outweigh the energy increases. People like daylight, and you see the studies of increased productivity from good daylight. This is a study that Nick and I did. I'm not sure I have the right charts up there or anything, but this is the Sensi Distribution Center. We looked at 3 different, well, there's probably even more than 3 different skylight configurations, and increasing skylights and how it affects the daylight in the space in terms of the foot candle level, but also the energy savings. And so we found, this is what we said, the energy went down right away, but as we kept adding skylights, it started to go back up. So we need to decide what we're aiming for there, if we want to make that daylight perfect, or if energy savings is the driving factor there. All right, electrical DD, kind of alluded to this before, but the big box retail, there's a ton of interior lighting in there. We need to get electrical on board. They need to help us out with that. And the same with the southern border station. In that particular case, we didn't know the exterior lighting until the very end, and we weren't hitting our energy design goals. And we found out that the site boundary includes this long driveway and big parking lot, and we saved a ton on exterior lighting, and that got us the savings we needed. So yeah, just another plug to get your electrical engineer involved as soon as you can. All right, mechanically, this is, like I say, the most involved portion in the DD, I think. It's also kind of difficult to show on a presentation here because there are so many components. Just a screenshot of a model of these components. So you have all these fans. Every little point here is something that can be tweaked a little bit to make it just a little better. A lot of things to play with. So work with a mechanical engineer. Look at each of these different points. Look at the actual equipment. Try not to use just defaults anymore. So this is an example of that. We had a fish lab up in northern Michigan, and they need a lot of processed water for their fish tanks, and we need to heat and cool that processed water to keep the fish happy and do their experiments. So we're bringing in water from the lake and into this big 1,000,000+ gallon storage tank. We figure there's got to be something we can do about it. But start off with the baseline system, which is just a boiler cooling tower that feed a heat pump loop, and then each of these heat pumps distributes the heat either to the fish tank or the space. So then we say, well, what if we have a central heat pump that has a loop in the big water storage tank? Then we can have this heat pump running, and we don't have an inefficient boiler running all year. And all right, we're saving a good amount of energy. But then we look at, so that's this here, this central heat pump, and that kind of tempers this loop. Well, then we think, well, why do we need that? Why do we bother tempering this loop? So we take away that central heat pump, and then all the individual heat pumps take care of the load. So there's different considerations with each of those. Can the little heat pumps handle the temperature range and things to look at like that? But be creative with your designs. I think it helps to draw out a schematic like that and figure out how the system's working and how can we change it. Just still kind of a high-level analysis. All right, so end of DD, we have some results. Time to inform the team. It's kind of our last chance to make some changes to get to our goals. Kind of a fourth quarter huddle here to make it happen. Get those. Yeah, another big piece of that is getting your ideas on paper. A lot of times we'll talk about it, and everybody says, yeah, this is great, we'll do this, and it doesn't end up on paper, and it doesn't work out. So make sure that somehow these ideas are getting on paper into your design. So we're talking control sequence tweaks. We talk about doing specs all along the design process, so ideally your specs are done early, but I don't really see that happening very often. Most often the control sequences are happening towards the end of the project. And that's okay. We need to be constantly tweaking our controls, and model is a great way to do that. What happens if we tweak this a little bit, change our set points, put in a reset schedule, something like that. Final lighting design will come in at some point. Your electrical engineer will have all the lights laid out, and you can add them up and put that in. That'll have an impact on the model. And then at some point you're probably going to have to deal with VE items. You have this great efficient design, but owner can't afford it, so we got to take something out. What's the most cost effective and thing that will affect our energy savings the least. And we're going to finalize our results and document them for whatever the we're doing LEED or Green Globes or just the owner. And then in this phase, I like to call it model commissioning. We're basically building, it's a model building. It's a computer model of your actual building. And it has the same problems as a regular building would have in terms of things not working right. So you need to go in there and make sure everything's functioning as you expect it to. And then the yeah, we've run into that a couple times where we had this cool M&B system laid out, and then we found out 2 years down the road when we have all this data that we can't access it and nobody knows how to get into it. So make sure that there's a plan in place for that. Okay, so model commissioning. The more complex your model or your building is, the more complex your model is. Pretty simple. But your software does exactly what it's told, but it's not always what you think it is doing. Make sure you test it. And also your modeling, what might look like a modeling error could be a design error. So if you're going through and checking everything, you notice a mistake, check it out, but then go talk to the engineer or whoever, say, all right, I don't think we have enough capacity in this system, and maybe there's a design error in there too. Whenever you have a workaround system, something that can't be modeled explicitly, check it out, make sure it works. And really this, I think, is the best way to learn about building physics. There have been a lot of times where I've made a tweak and the opposite result that I expected actually happens. For example, we were working on a project in Montana, and they were improving the envelope. So we sealed up the building a little bit better and reduced our infiltration rates in the models, and their cooling energy went way up. We couldn't figure it out. But basically the infiltration is working as an economizer. It's cool in Montana, so that cool air leaking into the building is actually helping the energy in that particular case. But yeah, anything you're unsure about, dedicated outside air systems are a big one. They usually don't work in energy models. Nobody does it right, so check them. Here's an example of what I'm talking about. So we looked at those hourly results earlier. Easy to spit out. So here's just a sample day. You see we've got a cooling load at 3 o'clock in the morning. That might be okay, but check into it. Well, why do we have that cooling load? Is our night set back working? And the other thing is, why is it cooling at 43 degrees? Shouldn't our economizer be taking care of that? Maybe it's an IT room or something on that chilled water loop, but something you need to look at. And then you see the ones all the way down the heating water, meaning our heating water loop is running all the time. It's probably not ideal. Maybe that's just the way it has to be, but check your inputs there. And this is just a small portion of what you can get out of those hourly reports. There's really a lot of information you can look at. And once you find an issue like this, maybe go look at your percent outside air, see if your economizer is working. But just take a look at that. All right, so we're done with CDs. Time to document our results. You guys probably know that energy modeling meets the requirements of LEED, Energy and Atmosphere Prerequisite 2, and Credit 1. There's other ways to get around that, but you get a lot more points in the model. Green globes will require an energy model. EPACT, there's a tax incentive for EPACT, but it's also a federal government requirement. And so any federal jobs, you're going to have to do an energy model and show their compliance with EPACT. Sometimes they don't catch you on that, but you need to be ready to do that. And then time to move into measurement verification. Our energy model is no longer affecting the design. So Chuck and I were actually talking this week about good measurement verification results. It's most of the time it's not because you made good assumptions in the model, it's because you got lucky. It happened to use the building the way you predicted, and I guess the building type has a big influence on that too, but there's a lot of assumptions that go into it, a lot of luck involved. When you're modeling and you're doing measurement verification, try to get as much data as possible. Talk to the building owner, see how they're using the building, see how many people are in there, how many computers. The more information, the better. It may make it hard to calibrate the energy model, but it's going to be a more accurate model at the end. Communicate with the building operator as much as you can. He'll be able to show you BMS readings and things like that, so you can get your actual building schedules and your energy usage. A lot of times that's hard to do. They won't let you into their systems, but if you can, take a look. And then time to calibrate the energy model, see where we went wrong and fix it. And we go back to the actual weather data. One thing to point out, I mentioned this earlier, but past BSUG guy just came out with a set of actual weather data. Go get that from him from White Box Technologies. I think he presented a year or two ago. So here's some actual data. This is a bank we did in northern Wyoming. And this was kind of a success story. We happened to be real close to what we predicted. The bars are the actual energy usage, and then the blue is my original energy model for LEED, and then orange is calibrated. there's different ways to calibrate the energy model. I've been going off of just a typical 10% monthly error range. I know Jake has been working on some other ways, the ASHRAE 14 or something like that. There's some good guidelines for you, but yeah, a bank and office type of building is a little bit easier to predict. It's kind of an 8 to 5 schedule. So pretty good results there. But you can see, even in the data, there's some big fluctuations. Who knows why they jumped up. I actually had to cut this off. The energy went way up in this month. I'm not sure what was going on there, but they're just starting out the building here, and there's some peaks and valleys in there. There's a lot of variation in actual buildings. So even if your model is calibrated, it may or may not be correct for future data. And this is the CSI Health Sciences building out in Twin Falls. And this is one where we were kind of way off. Our total energy was pretty good, but you can see the blue there. We expected them to be using it in the summer, and they just didn't. They may in the future, they may not. But you can also see with this is a university classroom type building for nursing students and that sort of thing. But there's a lot of fluctuation month to month here. And right about here, I started noticing there's actually the fan energy. In this one, we have 3 different meters on the building that I'm getting on a monthly basis. And the fan energy just started spiking. And in this case, I was able to talk to the building operator. He said, yeah, we're starting to use the building until 10 o'clock on a regular basis now. So that's what happened with the spikes. So stuff like that will happen in your buildings. You can't expect the building owners to use the building the same way all the time.
So I have a quick question about
Sure.
these two projects. So once you calibrate the energy model, are you actively using it with the building operators to check like the tolerances between the two, or is it mainly just exercise and energy?
This one we are. So I'm still getting energy on a monthly basis. And if I see something weird, I'll talk to them about it. I can't get any data for December. I've had to fake it in. Nobody's around for Christmas. And they don't keep it for some reason. But yeah, we're trying to do that as much as possible. This bank project, we haven't had good luck getting actual bills and stuff. So this was an example where we had a sophisticated M&B system set up and just didn't get the data. So we're working on utility bills there.
Did you usually use utility data analysis on that bank one?
Yeah. Yeah, so in conclusion, go out and enjoy the rapids, jump into the energy model, know your line, pick where you want to go, help everybody else through it. Hopefully we all come up upright in the end, so enjoy it. With that, I'll leave it open for questions.
I was wondering with that associate project, is there any architectural or little features that you noticed that kind of surprised you that affected the energy model?